This is CPE 133. This is Chapter 9 in the Free Range Verilog Foundation Modeling book. We'll do this in a couple parts, starting with, of course, Part A. So we'll be talking about comparators and typical subject, but we'll be getting to signed numbers and how Verilog handles signed numbers. And here's our disclaimer. Once again, you're not going to learn Verilog by watching videos or reading books. You're actually going to have to sit down and crank out some circuits. So I encourage you, crank out some circuits. So comparators, we consider it one of the foundation modules. Once again, conceptually simple circuit, but the implementations become somewhat complex. So very easy to use behavioral modeling to describe them, and so that's what we'll be doing. So this is a classic circuit. It is combinatorial. The big issue here is that we try to avoid, but we will have to address in this chapter is, are we working with signed numbers or are we working with unsigned numbers, which is of course going to affect the comparisons, because essentially what's happening here is we're comparing one set of bits to another set of bits, which is essentially the A and B bits here, and then we're establishing some status accordingly. The issue is that how is the hardware, or how are we or someone, how are we going to interpret that set of bits, whether it be a signed number representation or an unsigned number representation. So it could be a couple different ways. It's really up to you, the modeler, to control what goes on. We try to work with only unsigned numbers, I guess, but it's inevitable you have to work with signed numbers. So you got to understand how Verilog handles it, and that's what we'll be working with in this chapter. So Verilog has a bunch of relational operators. You've seen a lot of them up to this point. You've seen the equality operator, which is double equal sign, but it also has another set, a bunch of other operators here. Nothing exciting. So essentially stuff as you have seen it before and other math applications. But interesting here is this operator. You've seen it before. That's actually a non-blocking assignment operator, but it's also reused as a less than or equal to operator. So essentially no big deal. It's the synthesizer decides what it's doing by context. So once again, these comparisons here generate a 1-bit result, with 1 being true and 0 being false. So we're going to drive our discussion here by just using an example, and this is going to be an example of modeling a 10-bit comparator. Okay, so there's two 10-bit inputs. We're going to decide arbitrarily if A is greater than B, A is less than B, or A is equal to B. So this is something that is kind of understood in comparators, that it's kind of A related to B and not the other way around, such that A is greater than B, A is less than B for these given outputs here. And it's typically you have to state that, and maybe you should state it to be completely unambiguous, but that's the operation here. We're going to be A less than B, A greater than B. It doesn't really matter with the equals, because that's always the same. So this is one solution we have here, and let's see if there's anything interesting in this solution. I guess there's a couple interesting things. First of all, we've declared both inputs on the same line. Not a big deal. Usually I like separate lines for A and B, but I'm trying to save space here. The sensitivity list includes all the inputs, which is A and B. And here we go. So there's going to be 3 relational operators. Here are the 3 relational operators, which is equal, greater than, less than. And under each of those operators, we assign the appropriate stuff. So if A equals B, equals get assigned to 1, and the other 2 variables here gets assigned zeros. And you can see that happen for each of the other if clauses, and nothing exciting there. But the important thing here is that in each of these if clauses we have assigned all 3 outputs, and thus we avoid generating a latch. Okay, additionally here, I like to include else statements in this thing to tell the world that we are modeling a combinatorial circuit, which means they always have to have a catch-all on a combinatorial circuit. So I like providing one there, and that works for me. That's one way to do this circuit. Only other issue I can think of on this is that, remember, there's if clauses. It's going to go through these in order until one tests true, and then after one tests true, it does not check the other one. Essentially, the way it's written, this always block terminates. I actually don't like that solution as much as this solution, and it's essentially everything's the same except for the body of the always block. So what we have here, and this is super typical in Verilog modeling or just HDL modeling in general, that at the always block kicks off. Something kicked it off. Essentially, it was a change in the A and B input. So the always block kicks off. And so what I've done here is taken all three outputs and assigned them values inside the always block. Okay, now they have values that will never generate a latch because all the outputs have been assigned. Okay, so now it's going to step through here. If A equals B, what it does is it overwrites this assignment that it made here. Now this works quite well because actually this assignment is not really made. It's actually scheduled to be made. It doesn't get made until it hits the end of the always block, essentially when the always block terminates. So super important operation. What this means is that I can, inside an always block, I can assign the outputs as many times as I want. The only one that makes any sense is the last one that got assigned. So initially we assigned this equals here, and then we reassign the equals as part of this if clause here. That's perfectly valid. That's what you're kind of expected to do when you're working with these circuits. But the important thing is values are not assigned. They're scheduled to be assigned. And the assignment doesn't happen until the module terminates. Essentially, the always block terminates. Once again, I like this solution. I like this approach better than the last approach. Certainly less code, and to me it just makes more sense. It is a combinatorial circuit, so I like to include an always block, a catch-all statement in this. And there's my catch-all, and I just toss something in there just for filler. Next problem, we're just going to design a n-bit comparator. So it's going to be a generic comparator. It's going to make code reuse more possible. Certainly I don't want to design a 10-bit comparator if I already have an 8-bit comparator sitting there. That would make no sense. I would try to keep this as efficient as possible. So what we're going to do is generate a parameterized design for the comparator, and we're going to call it an n-bit comparator. So this is the solution. Once again, it looks very much like the previous solution where we assigned all the values up at the beginning of the always block. But the difference being is that I tucked a parameter inside the definition right there, and that parameter is n, and that parameter is going to default to 8. Okay, so here's your n right here. So if n it does equal to 8, I have an 8-bit comparator, and that's the idea here. This is the width of the data that's being compared. So that's the only difference. The issue here is I have a couple options when if I need a 24-bit comparator, for example. Here's my instantiation for the 24-bit comparator. Essentially, this value right here overrides the default value, and of course these fields right here are just junk. I'm going to fill those in to make them work in my model. Once again, you do not want to, if you're not using one of these outputs, for example, you do not get rid of it. You just leave the outputs or the interior of the parentheses blank. We're talking about comparators here. Worked great, yet they were inherently work for only unsigned values. So next we're going to delve into working with signed and unsigned values in the next part of this lecture.